Hi, everyone. This time we're going to talk a little bit about electromagnetic induction. Electromagnetic induction was actually discovered by a fellow named Michael Faraday, who was an Englishman. Fascinating background. He had very little formal education, and through a long series of circumstances, he ended up working in a scientific laboratory. And Faraday was a great tinkerer. He did not possess a big background in calculus and higher level mathematics, but he had a very astute mind. He was very, very practical and one of the greatest experimental physicists that ever lived. Piece of trivia: on his desk, on Albert Einstein's desk, was a picture of Michael Faraday, Sir Isaac Newton, and another great scientist, James Clerk Maxwell. So it kind of gives you an idea of how well respected Michael Faraday is in the history of science. One of the things that Faraday discovered was how to produce electricity. And we're talking about the electricity that runs your lights, cooks your food in your microwave, runs your Xbox, and helps heat your home. And he figured out that you can produce an electric current by moving wire and magnets relative to each other. And this process of moving wires near magnets and producing electricity is what we refer to as electromagnetic induction. So Ørsted had determined that if you have a wire and it contains an electric current, there is going to be a magnetic field that surrounds that wire. So electric current will produce a magnetic field. What Faraday found was that if you have two magnets, there is, of course, a magnetic field between those two magnets. And if you take a piece of wire and you move that wire, just pull that wire through that magnetic field, an electric current is produced in that piece of wire. So once again, there is that relationship between electricity and magnetism, and magnetic fields help make electric current, and electric current helps produce magnetic fields. One of the most famous experiments done by Faraday looked something like this. He had a metal ring. So think of this. The thing that in my life that this reminds me the most of is like a big rubber donut that you would use as a dog toy, but this was certainly not rubber. This is a very large iron ring. And a large iron ring is surrounded on one half. It is totally encased with an insulated wire. So you've got an insulated wire. Part of that insulated wire leads back to a switch, a power supply such as a battery, and then the other end of the insulated wire. Now, totally not connected, these two wires are not physically connected at all. There is another piece of wire that insulates that coils around the other half of the metal ring. And this other wire is connected to a device called a galvanometer. Now, a galvanometer is very much like an ammeter. It detects current. The thing about a galvanometer that is handy is that a galvanometer can swing to the right and to the left and detect current in one direction and detect current in another direction. Galvanometers are not calibrated with specific units, but they are very handy if you want to detect electric currents in both directions and you want to see that detection of current. In lab, I use a lot of galvanometers when I'm just trying to detect a small current. So here's what Faraday did. He closed the switch. When he closed the switch, I think I'm going to change my pen color for a moment here. When Faraday closed this switch, what occurred was the current went through the left-hand side of this wire. And when the current went through the left-hand side of a wire, it produced a magnetic field. This magnetic force field went over and across it emanated out into space in 360 degrees in all directions. As that magnetic field passed over the right-hand side of the donut, it generated a current in the wire. And this current was detected over here on the galvanometer. Now, the interesting thing is the current was only produced when the magnetic field was turned on. When the switch was closed, when the current flowed, that's when the galvanometer twitched. After the switch was left closed and the current was flowing at a nice steady rate, the galvanometer went back to normal. So it was only when the magnetic field was changing that you got this surge of current on the other half of this circuit, even though these, both the left half and the right half, were totally not touching each other. There is no wire connecting the left and the right hand side of this. They were totally not connected in space. What occurred again was that, and I got to erase a little bit, Mary's gotten a bit messy here. The other thing that happened was that Faraday found when he again went from a closed to an open switch, the magnetic field that had been all over in 360 degrees in space, that magnetic field died. And when the magnetic field died, the magnetic field moved over these wires. Again, it produced current in this loop. The galvanometer twitched, but it twitched in the opposite direction. Well, he determined that it was a changing magnetic field that actually produced current in the wire. So it was only when the magnetic field was being turned on or turned off that the current was produced. This electromagnetic induction, it was inducing the production of an EMF, an electromotive force. Well, an electromotive force is measured in volts. He could produce a voltage that we all know is measured in joules per coulomb, which means it can do work. A voltage could be induced by simply changing a magnetic field. This was a huge discovery in the history of mankind. And this led to the creation of electrical generators. An overly simplified sketch of what an electrical generator is something like this. You have a magnet with a north and a south magnetic pole. There is a coil of wire. This is ultra simplified because there is one loop of coil here. And when the coil of wire is sitting still, well, nothing is going on and no current is developed, no current is produced. But if you add motion, if you make this coil rotate round and round and round, what happens is this. There is a magnetic field between the north and south poles of this magnet. As the coil of wire is made to rotate through this, it cuts through all those lovely magnetic field lines as it goes looping round and round through here. That is actually making the electrons flow in this loop of wire, and that produces an electric current. It is a magnificent thing. So this is inducing current in the wire, just like a woman who's expecting a child is sometimes labor is induced or made to happen by moving a coil of wire across a magnetic field. An electric current can be induced or made to occur. There are two different kinds of electrical generators, those that produce direct current or DC generators, and those that produce alternating current or AC generators. If you recall, DC current is used most often by computer chips or electronic devices. Alternating current is what comes out of your electric wall sockets in your home. Things like fans and blenders, drills, washers, dryers very often use AC. But in a generator, motion is the input and output, you get electricity. Now, the difference between an AC generator and a DC generator, they are very, very similar in design, and we're talking about ultra simple here. Now, if you're actually going to go into production making generators, of course it's a lot more complicated, but the simplest edge of design, you have a magnetic field in both cases, you have a coil of wire in both cases, and what happens, what is different between the alternating current and the direct current generator occurs in the brushes, and this is how the current is passed from the axle to the actual galvanometer or ammeter, or where that current is going to be used. In a DC generator, there is a split ring commutator. There is a split ring that keeps all the current flowing in one direction. And in an AC generator, the current is allowed to flow in one direction when the loop is going up, and then current flows in the opposite direction when the current is flowing when the loop flows in the other direction. An electric motor is, on the very simplest terms, a generator run backwards. You input electricity and you output motion. So you have a shaft, you input current through your loop of wire. When you put current through that loop of wire, it is going to create a magnetic field around it, and that magnetic field is going to interact with the magnetic field that occurs between the two magnets. Two interacting magnetic fields are going to produce a force, and that force is going to cause a torque. This loop is going to push like this, and you're going to get rotation. That rotation is going to be motion, and hence the motor can run everything from your fancy Tesla car to your electric fan to your blender when you're making margaritas. I'm going to ask you to watch a video or two with three-dimensional movies of how this works, and